In section 1.3, we're going to be talking about the states of matter. Solid, liquid, and gas are the three states of matter that we're all familiar with and that we encounter on a daily basis. So let's take a look at their properties. So solids do have definite shape and they do have definite volume. So what that means is that if a solid were to be placed in different shaped containers, then the solid would still retain its shape. And it would also still retain the volume that it has because solids take up a specific amount of space. The particles in a solid are going to be moving very slowly because they do not have a lot of energy. In fact, they're going to be in a specific location. They're going to be structured in a specific manner, and they'll vibrate in place, much like we see in this image here. So the particles are going to be packed closely together. It's very dense for most solids, so they're very densely packed together, and they just kind of shake in place. And there's a strong intermolecular force between these particles, which means they're all kind of tugging on one another and they're strongly held into that location. So there's a lot of different types of solids that you encounter on a daily basis. And these pictures just show you a few different images: rocks, soap, books, tables, just about everything that we encounter on a daily basis is going to be a solid. There's two different categories of solids: crystalline solids. So crystalline solids have a regular repeating pattern. So they are going to be in a specific crystalline lattice shape, like you see here. So this is what a crystal lattice would look like for a grain of salt, for example, which is this kind of cubic shape, much like pyrite cubes, and snowflakes, and my favorite element, bismuth. It makes these beautiful rainbow colors, but also is very specifically crystal structured. Beryl is another example, which emerald is an example of a type of beryl, and they have very specific shapes. So there's lots of different types of crystalline solids, lots of different crystal shapes, but they all have specific geometric structure. Amorphous solids, however, instead of having this crystal lattice, amorphous solids are going to be packed closely together, so they're still very dense, but they're a little bit chaotically organized. So they don't have a specific organization. They don't have a specific pattern. And usually amorphous solids are going to form because of a very quick cooling of the material as it's forming. So an easy way to remember amorphous solids is your stems. So A means without, and morph refers to the shape or form of a structure. So it's without a specific structure. And sometimes I like to refer to amorphous solids as kind of globby solids, and they seem to be usually pretty quickly impacted by heat. So, for example, if you were to light a candle, you light the candle wick, and it's going to heat up the wax around the candle, and that'll start melting. Bubble gum, you start chewing it up, and it kind of melts into this globby mixture that you can blow bubbles with. Cheese, cotton candy. So all of these are examples of solids, but they are very amorphous. Liquids. So our next state of matter. This one does not have a definite shape. So whenever a liquid is put into a container, it's going to take the shape of the container. Liquids do have a definite volume, so they do take up a specific amount of space. The particles in a liquid are going to flow freely, so that means that they do have enough energy to move around, but they don't have enough energy to move around a whole lot. So I put that they have medium energy. So they kind of, based on their energy, fall in between solids and gases. So the particles move freely, and they're going to be fairly closely packed together. So they still have a pretty high density. They're not as dense as solids, though. And one thing that you notice about liquids, when you pour a liquid into a container, it's going to start filling up the container from the bottom. So if it's poured into a cup, if you have water, for example, that's poured into a cup, then the water, since it's a liquid, will start filling up the cup from the bottom up. And that's because, of course, gravity is pulling that liquid downward. A lot of chemicals that we use in the chemistry lab will be liquids as well. So, one term that applies to liquids is viscosity. Don't get that confused with the word velocity. Those are two different terms. So, viscosity is a liquid's resistance to flowing. So, if you have an item that has high viscosity, then that means that it is going to be really resistant to flowing. That's going to be usually a really thick liquid and it doesn't flow very easily. Molasses is an example. A lot of lotions are examples. Honey is an example. So these are things that are very high viscosity. Like if you try to pour syrup onto pancakes, it takes just a minute to kind of get going. And that's because it has high viscosity. It's a little bit resistant to flow. It flows very slowly and is very thick material. Whereas low viscosity means that it's very watery, it's very runny, it's going to spill really easily. So it does not resist flowing. So if you have a liquid that is a low viscosity liquid, that means it's going to flow very easily and it will spill very easily as well. So these are all examples of low viscosity liquids. If you tip over a Coke can, then all the Coke is going to spill out of it. Same thing with oil, water. So all of these are very thin seeming kind of liquids. And since they have low viscosity, they all will be able to flow really easily. So, what about these guys? These specific items here act a little bit weird. So, oobleck, which we'll make in one of our labs, peanut butter, ketchup, paint, like acrylic paint in these tubes, or oil paint, glue, a lot of hair products like gel or olive oil, different creams and conditioners. So, what about these? Are these solids or are they liquids? That's a great question, Miss Owens. So, those are non-Newtonian fluids. So, what this means is it's not a different state of matter, but they seem to kind of go back and forth between liquid and solid states of matter, depending on the stress that is applied to them. So, for example, ketchup, if you've ever used ketchup in one of these glass bottles, it's really difficult to get the ketchup out of the glass bottle. Like you have to turn the bottle upside down and like beat it on your hand, trying to get the ketchup out of the bottle because the ketchup is so thick. It has a really super high viscosity. So it acts like a solid. It stays in that container until some force is applied to it that makes it exit the container, which is why a lot of times you see ketchup in packets in small amounts or in squeeze bottles. Same thing with toothpaste. It acts very solid in the container, but you can squeeze it to make it exit the container. And by squeezing the toothpaste tube, that is applying a stress to it. There's some different types of non-Newtonian fluids. So one, the oobleck that we make in class using cornstarch and water. This is a dilatant non-Newtonian fluid. And so that means that the viscosity of the oobleck will act solid under certain conditions, will act liquid under certain conditions, and it only temporarily kind of acts that way when the stress is applied. So if you tap repeatedly really quickly on the oobleck, or if you punch a bowl of oobleck, then it really solidifies under that force. But if you just kind of like let your fingers soak into the cornstarch and water oobleck mixture, then it acts very liquidy. So it acts different depending on the stress that is applied to it, and only temporarily acts that way. So there's a couple other types of non-Newtonian fluids: rheopectic, thixotropic. So these will act differently depending on the stress being applied over a certain amount of time. So if you have a really high viscosity thixotropic material, then as you apply stress over time and more stress over time, then what happens is that kind of ends up getting a lower viscosity. It seems to go from a higher viscosity to lower viscosity. The opposite of that is rheopectic. And an example of that is egg whites. So if you're going to make meringue, that would go on a lemon meringue pie, for example. So if you have this really low viscosity, sort of watery egg white goo, and you continually mix it and mix it and mix it and mix it. Eventually, after applying that stress for so long and mixing it for so long, it ends up getting thicker and it ends up getting to a higher viscosity. And so that's another example of a non-Newtonian fluid. And those just kind of act differently. Sometimes they act like solids, sometimes they act like liquids, just depending on the stress that is applied to it. Gases. So gases do not have a definite shape. Gases do not have a definite volume. So the particles in a gas will spread out and they have so much energy that they literally are bouncing off the walls. They're bouncing around, bouncing into one another, and they spread out to take up all the shape, or the shape of the container spreads out to take up all the space that is available to it. So hot air balloon is going to be filled with gas that has been heated. Balloons, sodas have carbonation in them, and that carbonation is from this lovely molecule, carbon dioxide. And if you were to shake a soda bottle, then it is going to get it increases the pressure of those carbon dioxide molecules. So it gets all of them moving around really fast and again, bouncing off the sides of the container. So it's increasing the pressure. So if you've shaken up that container and then you open it immediately, then what's going to happen? That soda will spew and it will go everywhere. And that's because of the gas that's pressurized in there. And then we also know that the atmosphere is made of specific gases, mostly of nitrogen, about 78% nitrogen and about 21% oxygen. And then you've got like some hydrogen, carbon dioxide, water vapor, and argon, and some random other elemental gases in different amounts. So water is one of those different materials that we can find on Earth in all of the different states of matter that we've talked about, solid, liquid, and gas simultaneously. So we have ice, we have liquid water, and we have water vapor that's up in the air, water vapor that's in clouds. But we also have liquid water particles, particles of water that we drink as a liquid, also that fall from the clouds as rain, and also particles that are teeny tiny that are held within clouds stuck to dust and particulate matter. So we have water occurring in all three of these states of matter on Earth. So water is a pretty amazing material. So let's talk about some weird states of matter. So there are two other states of matter that you may or may not have heard of before. So plasma is our fourth state of matter. Plasmas act sort of like gases. They do not have a definite shape. They do not have a definite volume. So plasmas are actually going to be ionized, and they're positively ionized. So what this means is instead of it being like a gas and the materials, the particles in a gas just kind of moving around and bouncing around and being neutral, like most states of matter, most matter that we encounter are, it's going to be ionized. So it's going to be positively charged because most of the electrons have been stripped away. And so here are a few examples just to show you where you might be able to find plasma. So plasma is going to be a neon sign. So within the tube that is containing what we see as a visually bright substance, this tube is going to have a gas that is positively charged. It's going to be ionized. Another example is the northern lights, the aurora borealis. So if you've ever heard of that, that is due to plasma, and it's due to these electrons having been stripped away and positively charged ions. Plasma globes. So this is something that you may have seen of. A lot of novelty stores will carry these. The sun relies on plasma. So one example of the use of plasmas is something that's being explored with energy and being able to use that fusion and relying on plasmas, because plasmas can have magnetic fields and they also can conduct electricity. And so that is, again, something that's really different than gases. So these plasmas that do act similarly and in some situations to gas, they can also conduct electricity, which is why we end up having things like the auroras. And that's why we're able to see this coloration in neon signs. and Bose-Einstein condensate. So this is maybe one that you are not familiar with. So this is an interesting state of matter. It's our fifth state of matter. Bose-Einstein condensates are going to be on the opposite end of plasma. So we're going back to the solids, except for a little bit further on. So Bose-Einstein condensates, BEC, they have a definite shape, they have a definite volume. They were predicted to exist based on some research with some Bose statistics that were kind of developed by Satyendra Bose and confirmed by Einstein. And so this was created in a laboratory, synthetically created in the 1990s. And what happens with the Bose-Einstein condensate is that atoms are cooled to almost absolute zero. And absolute zero is super cold. It's like about minus 459 degrees Fahrenheit. So it's really cold. And what happens with these particles is that you're going to start out with a Bose-Einstein condensate. You're going to start out with atoms of rubidium. And then a laser is fired at the atoms of rubidium in order to make it get colder. So it basically pushes that heat energy away from it. And so it makes it get colder. And then to make it get even colder, then you end up having this radio frequency resonance evaporative cooling that is applied to the substance. And that makes it get colder and colder. And so it never reaches absolute zero, but it gets to a fraction of a degree close to absolute zero. So what ends up happening is you start out with this kind of arrangement of the rubidium atoms. And then as it gets colder and colder, the particles are all kind of smushed together. And these particles end up clumping together, and they're clumped together so closely that they're occupying the same quantum level. And so these particles are going to end up being kind of fuzzy. So if you were to look at it under a microscope, then these particles would look really fuzzy and you would not be able to distinguish the atoms from one another. So let's put this all together in this little graph right here. So if we're looking at the energy going from low to high energy, the Bose-Einstein condensates are going to have the lowest amount of energy. Solids would be next. We're continuing to increase in energy, so liquids would be next. The highest amount of energy that we're familiar with on a daily basis is going to be gases. And then the highest amount of energy or state of matter is going to be plasmas, which we would see like in the sun, for example.